Hello everybody, welcome to the homework help video for 533, the last new section of chapter 5. So we're going to be going over problems 117 to 123. Again, if you have any questions, please feel free to come see me before or after school. I'm also available 6th and 8th period to answer any of your questions. So in number 17, they ask if it's possible for the sequence t of n equals 5 times t to the n to have the term value of 200. So what they're really asking us in this problem is it possible for t of n to equal 200? And so what we want to do here is we want to set 200 equal to our 5 times 2 to the n. So I know that you guys don't know how to solve these problems exactly. What we want to do then is think about creating a table. And I know that I can use my graphing calculator to create a table. So that's what I'm going to use. So in my graphing calculator, in my y equals screen, I will put that explicit equation in there. So we'll have, sorry, my calculator froze. We have y equals 5 times 2 to the x. When I go to my table then, we can see that if we're looking at our output values, which is really what t of n is, the closest we get is when n is 5, t is 160, and when n is 6, t is 320. So we talked about how sequences today have very restricted domain values. And so what happens is that we know that that 200 has to fall between 160 and 320, but because our domain has to be positive whole numbers, the fact that it's not showing up on our table means that it's not going to be in there. There's no term, no positive whole number that when we plug it in for n, we'll get 200 back out. And so for 117, our answer is no. There is not a value. So in 118, they ask if it's possible for the function f of x is equal to 5 times 2 to the x to have an output of 200. And if so, what input will give you that output? So in this one, with our function, we're able to look back at our graphing calculator, and I'm going to change I want to view it. So if I were to just graph it, there's the function, but I'm looking for when my output's going to be 200. So I'm going to change my window just a little bit. I'm going to have my minimum start at -1 and go to, well, we talked about how it had to fall between the 5th and the 6th term, so I think leaving our max 10 is good. My y minimum, I know that the smallest number I have is 5, so I'll start that at 0. And then we want to go to see when it'll be 200, so let's put in like 300 and scale it by 10 each time. So let's see what this graph is going to look like. There we go. And so what I'm going to do is in my y equals screen, I'm going to put in 200, and I'm going to see where the red line and the blue line intersect. At this intersection point, I'm going to hit second and then calc, our second trace, and find the intersection, 5. And I'm going to get it, that little spider or cursor as close to that intersection point as I can. And it tells me that when x is 5.3219281, y will be 200. So we can approximate that value to about 5.32. So when we go back and they want to answer the question, if so, what output gives you? If you didn't know, if you put between 5 and 6, that's a good answer. And then the one we found that was a little bit more exact was about 5.32. Okay. And again, the reason we can't do it in 17 is because our domain only allows our x values to be positive whole numbers, but in a function we can have all real numbers. So anything with decimals will fall into that category. In 19, it says to consider the following sequences as you complete parts A through C below. So I'm going to erase what I have and then scroll down for us. we've got 3 sequences, sequence 1, 2, and 3. And then in part A, it says, assuming that the sequences above are arithmetic, so we're going to assume that they're arithmetic, that we're adding a constant. With T of 1 as the first term, find the next 4 terms for each sequence. And explain how you get that one, and write an equation. So what we're going to do is we're just going to write the next 4 terms in our equation. So I know that my next 4 terms, it looks like here, if it's arithmetic, I know I have to be adding by 4 each time. So my next 4 terms then, I will add 4, so it'll be 10, 14, 18, 22. If I want to write an equation for that, I'm going to need to know for the explicit, my 0 term. So I'm going to subtract 4 this way. So I get a 0 term of -2. So my equation is going to be the constant. So I'm constantly going up by a positive 4, so 4n, and then plus my 0 term minus 2. In sequence 2, I can see that I needed to subtract 12, so I'm going to do that every time. So my next term will be 0, -12, -24, and then -36. Again, I'm going to need to find that 0 term, so I'm going to add 12, which will give me positive 36. So my function, t of n, is equal to, that thing we're doing over and over again, -12 times n plus our 0 term of 36. And then lastly, in sequence 3, we're adding by 4 each time. I'm going to erase some of the stuff around it. We're adding 4 each time. So my next one will be 9, 13, 17, 21. To create the equation, I'll need to find my 0 term by subtracting 4, which will give me -3. So t of n will be equal to 4n minus 3. All right. Then in B, it said, would your terms be different if the sequences were geometric? Find the next 4 terms, and we're going to write an explicit equation for it, for t of n. So what we're going to do is look to find out what happens when it's geometric. So before we were assuming arithmetic. So when we're assuming arithmetic, our equations for t of n are in the form of mn plus b. But when we're geometric, it's going to be your 0 term, so t of 0, times your rate to the n. So our geometric equations are going to look much different than our arithmetic equations. For the first sequence, we have to figure out what we multiplied 2 by to get 6. Then we can see we need to multiply by 3. So 6 times 3 is 18. Then I'm going to need to pull out my calculator. 18 times 3 is 54. 54 times 3, 126. 126 times 3 is 486. So we can see we're growing at a very fast rate. And then likewise we still want to get our 0 term. So we'll divide by 3. So we'll just leave that as 2/3. So when I want to put together my explicit equation for t of n, I'm going to take my 0 term, which is 2/3, and I'm going to multiply that by my rate. So my rate is that thing I'm going up by each time, 3 to the n. For sequence 2, we can see that we need to divide by 2 each time, which is the same thing as multiplying by 1/2. So 12 times 1/2 is 6, times 1/2 is 3, then it's 3/2, and lastly, that'll be 3/4. We want to find that 0 term, so we'll multiply by 2, which will give me 48 for my 0 term. So when I plug that into the equation, t of n will be equal to 48, my zero term, times my rate, 1/2, to the n. Sequence 3 is a little tricky because we're trying to figure out what we need to multiply 1 by to get 5. Actually, that's not too bad after all. We know that we're going to multiply it by 5 each time. So 5 times 5 is 25. 25 times 5, 125 times 5, 625, and then times 5 is 3,125. And when we put it together for this one, again, we need to find that zero term. So we're going to divide by 5, so that'll be 1/5. So the equation we want to write is that t of n is equal to our zero term times our rate, which is 5, to the n. Then lastly in C, it asks us to create a totally different sequence for each pair of values shown above based on your own equations, right? The equation clearly using words or algebra so that someone else will be able to find the next 3 terms you want. So for this one, you're just making up your own sequence and figuring out the pattern and writing the equation so that you could do it. So just make up another one. Then in 120, it says for the function g of x is equal to x to the third, x squared minus 6x, find the value for each expression below. What I'm going to do, because this will be much easier, is this is in my calculator. So I'm going to pull up my graphing calculator, go to my y equals screen. And so when they say g of x, that's the same thing as y. So in my y equals screen, I'm going to put that equation. It was x to the third plus x squared. Oh, this is all being written as an exponent. So we just have x to the third plus x squared. That's much better. Plus, oh, and then minus 6x. The easiest way for us to do this is we're looking at all values from -2 through 10. So when I go to my table set, I'm just going to look at a table, which will give me the options a lot easier. I'm going to have my table start at -2, go up by 1 each time. And so we can see when x is -2, y is 8. When x is -1, y is 6. And then we need 1 and 10. So when x is 1, y is -4. And then to find 10, your calculator will allow you to continue to scroll down. So when x is 10, y is 1,040. Not too bad when you've got your graphing calculator. In E, it says to find at least one value for which g of x is equal to 0. So what we want to find is when this was equal to 0. If I scroll up, I see that when, uh-oh, did I put this into my calculator wrong? Oh no, yes, good. So we know that looking at the table, this was an easy find. When x is 0, y is also 0. Something else we could have done is plugged in or set the whole equation equal to 0 and tried to solve. Obviously, you guys have not done it before. It would involve pulling out greatest common factors. So definitely looking at our table was a nice, easy find for us. And then in F, it says if f of x is equal to, and they give it to us, find f of x, g of x minus f of x. So what we're going to do here is my g of x function was x to the third plus x squared minus 6x, and they want me to subtract my f of x function. I'm going to put this all in parentheses. They tell me that f of x is equal to x squared minus x plus 3. What I'm going to do now is I'm going to take and distribute this negative into everything inside the parentheses and rewrite it. So x to the third plus x squared minus 6x minus x squared plus x minus 3, and combine like terms. So I've got a positive x squared and a negative x squared. I know that that'll cancel out and go to 0. And then the other like terms I have is negative x and positive, or negative 6x and positive 3x. So when I rewrite this, I still have my x to the third, and then minus 5x minus 3. And that's how we do part F. Again, don't let this confuse you, this notation, this g of x minus f of x. You just want to plug in whatever g of x is, and then subtract away whatever f of x is. All right. Moving on, looking at 121. It says, write equations to solve each of the following problems. So all we want to do here is write it, unless they ask us for some more information. It says when, Leo Retro, a trendy commuter car, is brand new. It costs $23,500, and each year it loses 15% of its value. What will the car be worth when it is 15 years old? Ah, yes, a common problem. So the thing about cars is that they always lose value. The second you drive it off the lot, it loses its value. So this car, when it's on the lot, has a value. So if we were to think about this, this is our zero term. Before it's even driven off the lot, it's worth $23,500, but each year it's going to lose 15%. And so we talked about turning this into a decimal, and we know that we're decreasing. So we're really doing 1 minus 15%, which we know is going to be 0.85. And so when I want to put this into an equation, if I'm writing my explicit equation, t of n is going to be equal to my zero term, my 23,500. And then it's geometric because each year it's only going to be worth 80% of what it was worth the year before. So we're taking and multiplying each one by 0.85 and then to the n, letting n represent the number of years it's been. So when they ask us how much it's going to be worth after 15 years, all we have to do is plug in 15 for n. Again, a nice easy one to do with your graphing calculator. I'm going to erase the screen. So in our y equals screen, we're going to plug in that equation that we just wrote, clear out what we had before, 23,500 times our rate of 0.85, because remember it's decreasing in value, so it's going to have to be a number less than 1, and then we're going to raise it to the n. When I go to my table, what I'm going to be looking for is I want to find out after 15 years, and so when n is 15, our y is $2,052.8, and so our car is worth $2,052.80. So after 15 years, the car will have lost almost all of its value. In B, it says each year the population of Angel Island increases by 12%. The population is currently at, and then they give us a ridiculous number. What will the population be 20 years from now? So here we're looking at population growth. A very common feature is that for most places, your population should increase, except for places that are maybe going through hard times. So the population is usually an increased problem, and they do tell us that it's increasing. So we take our rate, turn it into a decimal, 0.2, and we know that it's increasing, so we're going to add it to 1. So we have a rate of 1.12. And they give us a starting number. So our starting number then will become our zero term. And they ask us what it will be 20 years from now. So when we put that into our equation, it will be our zero term, 14,365,112 times your rate, 1.12, to the n. And that will all be equal to your t of n. So that's what I'm going to put into my graphing calculator to solve. Need to erase the screen. And let's plug it in. Let's see if I can remember that number. 14,365,112. Y is equal to 14,365,112. And then times our rate, which is 1.12, to the nth, or to the x in your graphing calculator. And again, I'm looking for year 20. So after 20 years, the population now, again, it's growing, it's increasing. So we're definitely going to want a number higher than 14,000. That's what should be in the back of my head right now. So when I go to my table, I find that when x is 20, y is equal to, and they're giving it to us in scientific notation. That number is so large because that population is huge that they're putting it in scientific notation. But you can see that when I highlight it over changing it, right now it's highlighted on the x, and they're telling me x is 20. And then when we highlight over y, it'll give us a nice reading. And so we can see that y is equal to some ridiculous number. I'd have to put in 857,080.67. So over 1 billion people now live on Angel Island because the population is growing 12% every year. 20 years later is a long time too. All right. Lastly, oh no, sorry. 122 and then 123. It says it's an arithmetic sequence with t of 8 equal to 1056, t of 13 equal to 116. Write an equation and find t of 5. So because it's arithmetic, what we should be thinking of is the equation y equals mx plus b. We want to figure out what our slope is and what our intercept would be. And then we'll be able to make that prediction later. So what we really have here is the point 8, 1056, and the point 13, 116. So again, we have 8, 1056, and 13, 116. What we can do now is find the slope, our change in y over our change in x, and plug in our slope. So we should be doing 1056 minus 116 over 13 minus 8. When we do that, 1056 minus 116 gives me 940. I'm going to write that above. 940 divided by 5, which is equal to 188. So what we have then is a slope of 188. How that'll go back into our equation then is that y is equal to 188 x plus b. So we're going to need to figure out what our starting value would be. So to do that, we're going to pick a pair of points. I'm going to pick 13, 166 to be a little bit easier. So when 116 is equal to 188 times 13 plus b. So 188 times 13 is 444. And I'm going to take and then subtract away that 2,444 and get negative 2,328 is equal to b. So when we put that into our equation, let's keep that number in mind so I don't forget it. We have our slope of 188 times x minus our b term, which is 2,328. And so when they ask us to find t of 5, they're really saying what happens when x is equal to 5. When I plug in this 5. So 188 times 5 is 940 minus 2,328 will give us negative 1,388 as our final answer. So really what this problem is just realizing that you have 2 points. You have the point 8, 1056 and the point 13, 116, which is really just saying, can you find the slope between the 2 points and your starting value, which is stuff that you guys were working on in the first semester. Lastly, in 123, it tells us to describe the domain of each function or sequence below. So really what we're looking for is here, we've got a T of n, a T of n. These are our sequences. And then we've got functions. And the first function, we look at the domain, and we want to look for any restrictions. Now we talked about how functions can be all real numbers, and here it looks like I can plug in all real numbers. In B, we have a sequence, and remember, with our sequences for a domain, it's going to be whole numbers, so we need to have whole numbers as a restriction. That means we can't have any negatives or decimals. Looking at that next function, there is one restriction that we have to follow, and we want to see if there's any value that we cannot plug in for x. And hopefully what you guys realize is that we can't divide by 0. So for this one, it's all real numbers, except x cannot be equal to 0. So usually when we write problems like this, is if we just write that x can't equal to 0, we make the assumption that it can be literally any other number. Then looking at our sequence, same thing, except we can't have 0. So our domain for this one, when we talk about whole numbers include 0. So what we're going to say is the natural numbers. Natural numbers, or you can just say whole numbers except n is equal to 0, or n cannot equal 0. All right, that concludes the homework help video. Hope you guys have a great night. If you have any questions, please bring them to class, and we can talk about them some more.